Wow, it's only 2. So have sympathy for me. I have sympathy for you. Oh, by the way, about the exams, I really had intended to bring them back today. If I don't bring it back on Thursday, you can do whatever you want to me. I don't know. Just a lot. Every time I was about to get grading, something happened. This is tough because there's such. Here's where maybe it would have been better for me to come in with a computer and just give you a slideshow, because it's so hard to write this stuff down. Luckily, I've given you what I think are really good notes. I mean, the value and policy iteration notes are good. Good for reading. But because remember, I'm trying to get the concepts to you. I mean, looking at an algorithm is trivial. So this was the average cost optimality equation. You're trying to find a fixed point to this equation. And you can always normalize 8 star. So we take some point and we just presume that's equal to that, just so we remove one dimension. That's the reason. So we get rid of that unknown. That's the only reason. This is sometimes called a Bellman operator. And there's a missing bracket. Oh, no, there isn't. No, there isn't. No missing bracket. Just it is. It's called a Bellman operator sometimes. You'll see that in the literature sometimes. And so this boils down to a fixed point equation. 8 star equals T of 8 star. So it's exactly the same thing, just rewriting it. But once you write it like this, you say, oh, I know how to do that. I can apply successive approximation, Newton-Raphson, blah, 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 blah. And we did successive approximation last time. And I started to tell you about Newton-Raphson. And you guys were so awesome with all the questions, I didn't get around to saying much. It was a great discussion. It was fantastic. But the main thing about this guy, it's a minimum. See, for each, if you fix u, just period, then this is a linear function of h, right? Just fix u, right? It's just a linear function of h, all right? So think of this as a parameterized family of linear functions. And for each x, you're taking a min over that parameter, And minimum of linear functions is concave, period. So T is it's concave. And it satisfies some monotonicity properties. Which I'm not going to get into, which is one way to think about it. But it's, in a way, it's a shame I'm doing. At this point, I kind of wish we were doing the discounted case. If we were doing the discounted case, there'd be a beta there, and there wouldn't be this subtraction here, and it would be a strict construction, and strictly monotone in a very strong sense. Having that difference kind of screws up some monotonicity properties, but it does sort of have a monotonicity property. And so when we're thinking about Newton-Raphson, now, I know these are vectors. Just think about this might be h of x. We're just looking at one component of the vector h. But this is a h minus t of h. So this is concave. So minus t of h is convex. So it's a happy face. It's also piecewise linear. And so it's hard to draw this, but it's, wham, 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 wham. Maybe it'll go up again, I don't know. If it goes up again, we might be in trouble. That's unlikely. Forget that. In fact, let's not distract ourselves. Eight stars when this is equal to 0, right? By the way, that's the monotonicity I mean about, but that it doesn't come back up again. And in the discounted case, it's really clear that this is sort of monotone. And the average cost is not as clear. So I mentioned Newton-Raphson. What you do is, if you're given, again, I'll move this over. If you're given Hn, you look at a linearization of this function, and that gives you, setting that equal to 0 gives Hn plus 1. And when you emphasize the fact that this is piecewise linear, this sure looks trivial, and it sure looks obvious that this is just going to converge in 2 steps, right? Now I go up here, the approximation is the real thing, I'm done, and that's actually true. So it's just wham. And so at least 3 of you have done the homework already, and you saw the policy iteration just wham, it converges instantly. Now, what is the linearization? Well, the only problem with these things is that there's corners, So if I've got an H there, it's linear. Its linearization is obvious. And when you don't have when you have a corner, so let's just take that to be, maybe it's an initial condition for the algorithm. Let's take that as H naught. There's a lack of uniqueness, but concavity allows us to talk about subgradients. Okay, and that defines a subgradient to a concave function if I was in one dimension. Instead of a linear approximation, it's just a linear function which is above the curve everywhere. So what I mean by that is that A is a subderivative. Wait, hold on a second. We have subgradients. So so what I mean by this is the curve is above, the line is above the curve. How do you say that? I define a linear function such that t of h naught plus g, so there's h naught, there's h naught plus g. The value there is less than or equal to the linear function. All right.
Then if there was a convex, then you would say
Yeah, this is a sad face, it's concave, and so we're above. And if it's convex, it'd be a happy face, and you'd be underneath. And, yep.
I was going to say, as we've stated, that this is not unique, right?
And it's, well, yeah, at that point it's not unique, but you can see 1 is that tangent there, and 1 is that tangent there, and then you can take linear combinations of the two and get another one, convex combinations of the two. And in that case, that's all there are. And so here, as it turns out, it's kind of obvious in a way. That for any h, there's a policy, which is defined by the argmin. So I just go through and I'm going to let phi plus be a policy, which is a minimizer. What's that?
We're not, like, this isn't the true optimal.
Yeah, for any function. Yeah, because I'm going to, like, you know, this is h naught. I'd like to be able to get a linearization of that h naught. You know, I'd like, for any h naught, I'd like to be able to find A depends on h, okay? I mean, A is a subgrade A to h naught, so it's some function of h naught. Just like, you know, it's calculus, right? When you take a derivative, it depends on where you're taking the derivative. I hope it's pretty obvious that it's just these linear pieces that define the, you know, that define subgradients, at least the two obvious subgradients, one that's parallel to that face and one that's parallel to that face. You know, well, that's just defined using that policy. So A, and maybe I should put, actually let's put a naught there to be consistent. Let's stick it in, since I started with an h naught there, let's stick it in there. The A there, one example of A is just given by getting rid of the U and replacing it by this guy. And you can sort of see it graphically. Okay, so remember, T maps functions to functions, so that's got to be a function, that's got to be a function. It's a function of xu. And if I define this just to be this without the minimum, oh, wait. G. So if I make this definition, so a triangle on the top means that this is defined to be equal to that, then this satisfies that subgradient property. And there's a proof given in those notes, and I just realized it's just too tedious to go through and prove. But to get an upper bound, it's obvious. You just, here, this involves a minimum. You replace the minimum by this policy, and you get an upper bound, QED. I can say it in words so fast. Writing out in chalk takes forever. Again, you know, that H is equal to, set it equal to H naught plus G, okay? And then we have a minimum. Throw away the minimum and just plug in that policy. You get this bound. Do it. You know, not the second, but do it. All right. I expect you to remember this, to study this before the midterm, because it's boring to go through and explain. But you should read these notes. Yep.
So that's the policy. So when you say you plug in the policy, it's the policy you got from
this definition right there.
From
obviously, if I minimize over U, I'll get something. I might get something bigger if I plug in some arbitrary U. Now this is now, it's not arbitrary, but given that H is not equal to H naught, sticking in this value of U is going to give me something potentially larger. And that's why I get an inequality. And then you just do a bit of algebra, and you find you get exactly this. So it's nothing to it. And there you have policy iteration when you go and interpret this. So again, in policy iteration, this is a case where it's unique. The case I put on the board. You know, if I'd been here, I would have had that ambiguity. You know, I would have either chosen that one or that one. You know, for where to go next. So you can see there's a place where there's lack of uniqueness. You know, if this is not, I put a member sign there because it's not unique. Choosing the right one is not obvious. It's obvious on this blackboard that, you know, one is steeper than the other or something, but it's not obvious in code. But either one would work, you know. So if I was at this point, if I took that one here, I'd end up there. In 2 steps, I'd be done. And if I took the other one here, I end up at hn plus 1. I'd jump over this guy and I'd be there. So it doesn't matter which one you choose. Okay. All right. And what to do, you know? Let me just stop here. Is this all clear?
Piece of v plus that you have written there.
Yeah.
Before when it was piece of u, that implied that it was like the, you know, for the finite case, transition matrix. So
oh yeah. Oh, wait a second. Oh yeah. That's right. Hold on a second.
I'm just trying to understand what exactly.
Oh yeah. Right. But actually, hold on a second. Yeah. Thank you. Oh yeah, God, I'm sorry. I made a mistake. God, I made a terrible little typo here. You know, Aditya, you understand why I made a typo, right? We will talk about places where there's a function of x and u, but here's its function of x. There's a mistake there. Sorry. Remember, h is a function x. It's a value function,
yeah.
And th takes a function an x to a function an x. There's something called Q-learning where this will be a function of x and u, and that's what, you know, suddenly my brain went to Q-learning. So this is a function of x. So there was a typo in the boards. That's what maybe.
Oh, okay.
Yeah.
Maybe that will also enlighten the, so you have piece of e plus. Like
yeah. Remember that's a notational assumption I made. You know, I said that if I have a policy, I'll define a transition matrix, you know, by just substitution on the bottom.
Yeah. I remember like before when we had piece of u, we were thinking about it as like like a transition matrix for, you know, all possible, we're at this state, and these are all possible policy options.
Yeah.
Is this going to be like a strict like sub portion of that?
Yeah. Well, sort of you're picking up parts, because remember, if I use this policy, state feedback policy, my stochastic process X will be a Markov chain. It'll be a Markov chain with that transition matrix. Okay. That was the definition we gave. Okay. I don't want to review that, but you just basically, you know, this minimum over. Yeah. Well, never mind. I mean, yeah. Yeah. I don't want to write that down again, but there it is. And so, if you go through and and again, I realize it's just too boring to go through the steps. But if I go through and now interpret what I mean by saying that this is A, and I'm going to go and take a linearization and repeatedly go through the next steps, I'm just going to tell you the algorithm at this point, what you get from that, you know. I mean, you've looked it up, but I don't know. Or maybe it is better just to. I'm really struggling with this because it's not really that enlightening now to go through. I'll remind you what it means. I mean, so Newton-Raphson, we have, this is what we define to be t hat. And this is where somebody asked me about upside down triangles. This is the linear approximation to t, you know. And remember in Newton-Raphson, what you do is, yeah, I'm going to stick to the same notation as my notes here. So I'll denote phi n plus 1 of x to be the phi plus I get with this, with h0 placed by hn. Well, I'll just write it like that. Okay, so I don't have to there's no reason to write this down again. If you give me, instead of h0, hn, I can't keep calling it phi plus. I need new notation. So I'll call it the next policy. So at the end stage of the algorithm, I've got an hn. I define a new policy, phi n plus 1. And I've got then this linearization I'd like to cook up. And so I've got Pn plus 1 equals phi n plus 1, and I'm going to define a cost function. And so the linearization then becomes what? So oh my God, I see another typo. Constant terms can't still appear. Okay? So when I plug in g equals 0, I better get 0. So I kept the constant term, which I shouldn't have kept. Sorry about that. All right. When you do a linearization, any constant disappears. I mean, you always reality check. If g is 0, I better get 0, because we better be exact. Okay, so it's t of hn plus the linearization, which in this case would be Pn plus 1 times h minus hn, because that's what g is, that's the error. And then minus, this term here. I'll put an N there just to make sure that that's clear as well. Okay, so the nth stage of the algorithm, I just made a notational convention here with a policy. Notational conventions here and here. And what you find out is that that's the Newton-Raphson step, right? Is that you take your linearization and you solve a linear equation, right? Instead of the original nonlinear equation you wanted to solve here, right? And then you have to go and take all these things and plug it back in, all right? And everything cancels out. And this equation becomes Poisson's equation. So I'll put a star there. Okay, so the nth stage of the policy, I just told you the first steps, do this, then solve this, but this is just Poisson's equation. It's the miracle. There it is. You know, this, like I said, feel sorry for me. This is really hard to sort of get the essence to you without, you know, spending huge, you know, hours on this. But just by when you substitute those symbols right into there, everything cancels out, terms cancel. You can see in the notes, and you end up with this Poisson equation. All right. And so there it is. You just go through and do this, and as you can see graphically here, it flies. It converges so quickly. And so why would you ever use value iteration? Somebody asked today. It's because there, I told you can solve this using a matrix inverse. All right, there's a p tilde trick. There's all sorts of tricks to solve this. You know, but the complexity is an inverse problem. So the complexity can be pretty large for large state spaces. You know, inverting a matrix is, I don't need the complete inverse of some matrix. I only need the inverse applied to one function, which would be like C. So if there are D states, the complexity is like D squared. That's okay if D is 1,000. It's not so okay if D is 1,000,000. You know? So that's why this is maybe not used as often as you'd think. But I think also people are intimidated by it. This looks scarier. Well, value iteration is so trivial. And that's probably the main reason. So value iteration, each stage of the algorithm, the complexity is D with these steps. You know? So each step takes not much time at all. But geez, it's slow. It's incredible how slow it is. You know, which is strange considering, you know, how simple the problem is. Yeah. Yeah. All right. Okay. So it's good to know these tricks. Now, it's 2:30. I am going to sort of blow off algorithm 3, and even though it pains me to do so, but I'm going to tell you what it is and run, because we have so many things to do, and it just is too time consuming. So I'm just going to close in the next 15 minutes and tell you what the third algorithm is, unless there's a question. I don't know. It's not in the notes. Oh, yeah, so I'll write this down. So this is word for word from the notes. Well, the notes, it's all complete, you know. So the notes, you get to this stage, and a whole bunch of things cancel out, and you get that. It's so cute. But the LP stuff, I'll explain what that is. Yep.
What's the difference between x dot and x star?
Oh, did I use a star somewhere? They're interchangeable. Yeah, that's our. In the notes, you'll find I use star and dot over, and I regret that. I'm sorry. That happens. Yep. It's just a dot. X dot's a distinguished state. Yeah. Okay. Cool. So. So the third algorithm is a linear program. Now, why would I bring this up? In terms of complexity, you'll see it's the worst. But it's way more flexible than these other two methods. And it's a key to analysis in many cases. So it's just useful to know it exists. And then you'd think, why on earth would we have started with this? So here's the LP. I'll write it down. What's the notation I used in the notes? Actually, let's use the same note. We should now know it. I'm using this stupid linear programming notation. Let's be consistent with the previous lectures, even if you hate it. Gamma is a probably mass function on the states and actions. And G is a set of all possible steady state distributions on the pair. Oh, steady poem, yeah. Now that sounds pretty ridiculous. You know, we have to try to make this precise. Now, the thing is, how on earth would you characterize this? How would you even think about it? And especially given the fact that we know this is an integer programming problem. We know that in reality, the optimal policy we get is of this form. It's deterministic. U is not random. It's a function. I mean, it's random, but it's a deterministic function of state. So if you take G to be what you know it should be, this will become an integer program, and you'll be screwed. So what happens is you convexify. So here's how to construct G. See, again, you know, it's, you know, there's, in that simple how many policies are there for the homework? I think I asked you to compute how many. Did anybody work it out? What did you say?
I'm sorry.
In the homework?
Two or eight.
Well, yeah, no, how many? Yeah, so it's it's eight policies for that homework problem, something like that. So, you know, really, there's only 8 probably mass functions. For each policy, there's a probably mass function. So it's a minimization over 8 guys. Well, those are going to be the corner points of G. You know, and then we're going to take a convex hull. You know, because 8 works for a 3-state Markov chain with 2 actions. If you've got, you know, something more reasonable, you can have trillions of values. So it's absurd to think of this as it's a integer programming problem. You know, okay. So so the construction is you have to look at randomized policies. That's how you do it. So before I had a phi of u, Now phi is a probability mass function itself. Don't panic. Okay, so this is a convexification of the problem. Basically, because I can take convex combinations of policies now, and there's still a policy. That's the idea. It's a convex relaxation. So I start out with a finite number of policies. Now I've got an infinite number, but it's going to be. I'm going to make this thing convex. Okay, and what is a gamma? Oh yeah, hold on a second. Also, I'm going to use the same notation P sub phi. Yes.
Will we have to use Bayes rule because we're trying to infer the control action that was taken given the current state?
Not at all. No, we'll never need that. Oh, Bayes rule, yeah, Bayes rule comes up, but I mean it's right here. You'll see Bayes rule in a second. Yeah.
Okay.
If you're begging for Bayes rule, it's about to come. Yep, absolutely. Yeah, you're right. Bayes rule is about in about 36 seconds. You'll see Bayes rule. So here's an extension of a notation before. So before I plugged in, when phi was deterministic, I defined this P sub phi to be just P phi of x. And now, I mean, x given u. Can I flip it over there?
Yeah.
Sorry. X given u. I'm conditioning backwards. Maybe that's why you're thinking about Bayes rule. It's a probability. No, that's right. No, it's right. I just got myself confused. This is right. Yeah. Again, it's just, yeah. I hope you understand. Before I just plugged in, this was just 1 at one point. And so I just plugged in phi. Okay, so here is a class of G's. Oh, yeah. Kevin. Yeah, because you know, phi was just a, this wasn't, phi of u given x was just 1 at a particular input u. You know, it was probably 1. I'm going to pick this action if I'm in state x. Yeah. So yeah, it's a bit confusing. So then it was just think of it as a function of x. But here it's a probability mass function. For each x, I pick whether I go up the hill or whether I drive or don't drive. Maybe they're probably a half. Half I drive, half I don't drive. Now we know optimal policies in this setting won't be like that. Either I drive or I don't drive. I'm not going to flip a coin in the finite state space Markov chains we've looked at. This is just a way to get convexify the problem. Yep.
So are these phi of u given x and elements of G?
No, G is all possible steady state PMFs on this product space, on X. No, but I'm about to give it to you. So that's it. So typical G, or gamma. So gamma of xu is the probability of u given x. Times pi sub phi of x. There's your Bayes rule, where pi phi is invariant for p phi. Okay, so there it is. And it turns out that you can actually prove that if you, in a very, very strong sense, really stronger than you'd imagine, the set of all possible steady state probably mass functions, anyone has to be of that form for any possible policy. Not even necessarily any policy. It doesn't even have to be state feedback or anything, as long as it's not anticipative, as long as it doesn't predict the future. It's very beautiful theory to justify this. And what you end up with is that G is defined by some linear constraints. So, so see my book. I'm not saying you have to do this, but I mean, if you want more details, I have a chapter on this in my networks monograph. And G is just equal to the set of gamma. Just think of these as functions. The summation of gamma of xu equals 1. And then this invariance constraint can be written in another way. I'm not going to prove this for you. I'll give you the idea. Okay, so it turns out that it's a polyhedral convex set. It's a bunch of functions of x and u subject to the summation of our x and u is 1, or it better be for probably mass function. Its elements are greater or equal to 0, so a linear constraint. And this turns out to be equivalent to invariance. And you have to stare at that for a long time. I'm not going to bother doing it. But if you go through over here, this is, if you sum out over u, the sum over u is 1. So if you sum this over u, you'll get pi phi. So the right-hand side is pi phi. And this turns out to be exactly invariance, that this is equal to pi phi. Yeah, exactly that. So there it is, an algorithm. You can go through, and in MATLAB, you can take gamma as a variable, you know C, and have it solve this minimization problem subject to one equality constraint, another equality constraint, positivity constraints, and done. And that'll fly even faster than anything. I mean, you put this in a MATLAB for that problem I gave you. I don't know how many nanoseconds it'll take to solve. But gamma, you can think of it as a vector in R size of x times the size of u plus, at least there's a plus there. And so if you've got, I mean, wait, squared, right? No, just x. Yeah, just x and u. And so, so this can be huge as well. And so solving LP with, maybe 1,000 states and 100 actions, you might find MATLAB will scream. I don't know where this ranks in terms of what's better, Paulus iteration of this. I don't know if there's an answer out there. What's that?
The output of this algorithm.
Yeah, it'll give you gamma. Oh yeah, and once you get gamma, once you know gamma star, you're going to find out this is deterministic. It won't be randomized, especially if you use a simplex method, because it actually goes from corner to corner. The extreme points of this LP all correspond to deterministic policies, where this is just 1 or 0 for each year.
Why is it called linear programming?
What's a linear program? Oh, that's the definition of a linear program. The definition of a linear program is to minimize a linear function. It's a linear function of gamma. this is just a dot product, right? It's the same notation I've used before. It's a summation of gamma xu, c of xu. So it's a minima, I've got a linear function of gamma subject to equality constraints and positivity constraints. It's a linear program. So you can just write a couple lines of code and have it done.
Dynamics is the system here will get injected
through there, right there, through that equality constraint. You know, and that's something people in optimal control should know and love. You know, again, I always love saying this, but the most beautiful approach to optimal control is the minimum principle, where you treat the dynamics as a constraint. That's the whole origin of that. You forget about reality. You just call it a constraint, and you relax a constraint. You know, and you get the minimum principle. Here you're doing the same sort of thing. You know, you're solving an optimization problem, taking the dynamics as a constraint. It's really cool. Guess what the dual is, for those of you who have heard of linear programming. Well, it turns out the dual is the ACOE. Again, so I know some of you have no idea what I'm talking about, but there's every convex optimization problem has a dual. For linear programs, the dual is a linear program. The ACOE itself could be regarded as a linear program. And it turns out that 8 star, the relative value function, is the Lagrange multiplier for this constraint, or it can be, you know, yeah. Yeah, it's so cute, you know, it's adorable, and that's useful too. It's useful. You get ways of thinking from this. That's all. But you can imagine now. I mean, you can imagine once you have a toy like this, you can do all sorts of things. You know, I can minimize this subject to those constraints, but also have a constraint that some other auxiliary cost. You know, the number. I don't know, the number of liver patients, the average number that dies is less than so much. And the variance, well, the second moment of how many dies from not treating them is less than so much. I could put in all sorts of constraints, you know, in any kind of problem, and go through and do this. And what's really cool is if you do that, if I put in other constraints, if some of the cost functions have to meet upper bounds and lower bounds and go through it, then I no longer get a deterministic solution. I end up with the optimal solution is randomized. Anybody have a guess why? Well, you typically get randomized policies. If I impose additional linear constraints, so you know, basically I have other cost functions which I don't want to be too big. So maybe as well as maybe like one of them is the second moment shouldn't be too large. You know what I mean?
So we're imposing those as extra.
You could do that. That's what's so nice. You see, once you have this formulation, I can do that. I can put in have additional cost functions. You know. So. Yeah, I think you might have said it. You could say, and say gamma of Ci is greater than or equal to eta bar I for 1 less than equal to I less than equal to m. Okay, so I've got a C there, which is some cost. And I'll put less than, just because the cost less than. This could be the second moment. And maybe I should put a subscript. Sorry. Because it looks like I'm taking it to the ith power. But this C1 could be C squared. You know, I want the second moment to be not too big. And there could be other things about, every control problem has multiple objectives. All right? So now I'll ask it again. Why would the solution to this typically be a randomized policy? Well, without that, it is deterministic. One solution is deterministic.
We said the corners of G
Yeah. but I'm adding more faces. Every one of these makes a new face. Yeah, that's one way to think about it.
Because it's not, you don't have a, there's not some single solution, multiple.
Well, it's not quite that, but it's related to that. It's the fact that when I solve this, typically I'll get, many of these will be equality. You know? And the only way to get an equality is by doing some randomization. You know? It's basically that. It's basically that in order to get feasibility, I actually have to take a bit of you and a bit of you in order to make this work.
Is this
Yeah.
a valid policy?
Yeah, why not? Yeah, I'll just have to flip a coin. Probably a quarter I'll pick you, probably a quarter I'll pick you, and probably half I'll pick somebody else. And it's perfectly legitimate. And you can actually show how much randomization you can expect as m increases. You know, if m is 1, there's only, for each state, there's at maximum only 2 actions you'll choose. If m is 5, is at most 5 actions you'll choose. You'll randomize among 5 actions.
So I'm not sure I understand how phi is a policy, because it's a probability.
No, so I'm generalizing. A randomized policy is by definition that. So this is known as a randomized stationary policy. For every state X, I choose my U's with some independently, randomly, based on the path. Yeah.
You sample U.
Yeah, you'll have some. Well, yeah, there'll be some numbers here for every value of U, and I'll, you know, maybe one U has probably a quarter they'll choose it, another one a half. Yeah.
So let's say you have 2 U's.
Yeah.
So your phi of U given X. How does the given X come into play? I guess?
Well, right here I could say, for example, but it's always going to be this form. Ut is going to be some function of xt and zt, where zt is IID. It really is that. You know. So instead of ut being a function of xt, it's a function of xt and noise. That's all. Yeah. I'm introducing noise. And the only good reason for doing it, well, A, it gave me a convexification. I got an LP. And B, it allows me to go through and look at these more general problems. And so that's why I'm inflicting this on you. And there's so much more I'd like to say, but we have so many things to do. We'll have to just, you know, we can't go into much depth in this.
So how does that relate back to phi?
Oh, that's it. No. If U is a randomized function of X, you know, then I'll make you tell me what this is. You can work out this probability law if you knew that U was of this form.
Okay.
You know, U given X at t equals X, U is f of X comma noise. You know, and that has a probably mass function which is given by that. Yeah. That's what it means.
Okay.
Yeah. And it's that wonderful trick of convexification, you know, making something easy. Yeah. So that's the thing, is that this lives in a big dimension. The set of all policies is U to the X. The number of policies, it's U to the X, I think. So we sure wouldn't want to minimize this over all policies. You know, this might be. I mean, the convexification has a lot of value. It's All right, media adjourned. So here's where we are. Everything for the rest of the course is about learning. So we're going to bring in belief states and nonlinear filtering, so we can look at the partially observed case on Thursday. And I don't know if I even want to derive the damned algorithm. Go to Wikipedia and look it up. I'll explain the hidden Markov model in the nonlinear filter. But geez, it's such a simple thing. You can just, copy and paste the code off online anywhere you want. And they're just some conceptual points. When you have partial information, you can convert it to a fully observed problem. And that's when you get all the weird computer science stuff about belief states and features and all this stuff. So I'm going to demystify all of that. And I don't think we're going to spend a ton of time on that because it's the concepts that are sort of useful. But my God, I mean, this explodes when you have partial information. It explodes. All this goes through, but this becomes not finite anymore, you know, no matter what you do. A Markov decision process with 2 states, like the one you get in the homework, 3 states, 2 actions, that was partially observed, it becomes intractable. it's incredible. But you need ways to think about it. We're not going to solve them exactly, but we need tools to think about it. So we'll do that over the next, before spring break, and look at the linear case a little bit, and then fly into all these reinforcement learning algorithms, you know, and approximate dynamic programming. So it's all learning from now on. It's all, yeah.
So what's the accurate terminology here? Before we had a deterministic policy.
It's called a random. You have a race to know. That's called a randomized stationary policy.
Oh, right. And then before it was deterministic.
This is this is stationary, deterministic stationary policy, or people usually say stationary policy. Yeah.
What was the other one?
And this is a randomized. Yeah. And we will need this, by the way, when we get to, you know, Q learning or whatever, we actually will implement this. We need it, believe it or not. So it's not just a hack tool here. We need it, because we need it for learning. We want to explore a system. And if we use a deterministic system, we can't learn anything. Deterministic feedback, we can't learn anything. So we actually use this later on. Okay. Until next time.